Hello, in this learning dialogue, we are going to see how phenylethanolamine class of agonist have evolved, their pharmacology and therapeutic utility of these compounds. Now, after discovery of norepinephrine and epinephrine as prototypical compound, phenylethanolamine class of drugs have started to evolve and have been extensively studied. Epinephrine and norepinephrine are catecholamines, while here in this case we are talking about phenylethanolamines. Now, before proceeding further, for structure activity relationship of phenylethanolamines, you pause, think and write what are agonists. Now, while having a thought on agonist, here you may also have thought of antagonist. So agonists are molecules which are having affinity and intrinsic activity. That is, they produce effect after binding to receptor. While antagonists have only affinity and no intrinsic activity. So here is the structure activity relationship of phenylethanolamine. In phenylethanolamine structure, what are the minimum requirements for high agonist activity? Requirements are presence of primary or secondary aliphatic amino group separated by 2 carbons from substituted phenyl ring. Now amino group gets protonated at physiological pH and acquires positive charge and is involved in ionic interaction with the receptor. Further requirement is presence of hydroxyl group on carbon number 1 or beta carbon. Since carbon number 1 or beta carbon is substituted by hydroxyl group, it becomes chiral. So, what should be the configuration for maximum activity? This beta carbon or carbon number 1 should be present in R absolute configuration. So R configuration is the requirement for high agonist activity. Now we are going to see what are the effects of substitutions indicated as R1 on amino group, R2 on carbon number 2 or alpha carbon, and R3 on the phenyl ring. We'll first concentrate on R1 substitution on amino nitrogen. When we look at the structures of norepinephrine, epinephrine, isoproterenol and cholesterol, you will find that R2 and R3 substitutions are same, while there is difference in R1 substitution. Norepinephrine is having hydrogen as R1, epinephrine is having methyl group, isoproterenol is having isopropyl group, while cholesterol is having tertiary butyl group. So what is the effect of this substitution pattern on activity? As size of R1 increases, alpha activity decreases and beta activity increases, while tertiary butyl group gives selective activity at beta 2 receptors. And this also explains that beta receptors have large lipophilic binding pocket. Now R2 substitution on carbon number 2. The example taken are alpha methyl norepinephrine, which is having methyl group at carbon number 2. Now presence of methyl group in alpha methyl norepinephrine makes it active at alpha and beta receptors, while ethyl group as R2 reduces activity at alpha receptor and increases activity at beta receptor. Presence of small alkyl groups at carbon number 2 also slows down the metabolism by monoamine oxidase, but still it have little effect on duration of action in catecholamines, since catecholamines still remains substrate for COMT, that is catechol O methyl transferase. Now important point is, if there is a substitution on carbon number 2, that is alpha carbon, then what should be the configuration for maximum activity? Stereoisomers with 1R, 2S configurations have maximum activity. That means C2 should have S configuration. Configuration at carbon number 2 is having great effect on binding to the receptor. Effect of R3 substitution. 3,4-dihydroxy substitution on phenyl ring gives excellent activity at alpha and beta receptor, but have poor oral activity as they are rapidly metabolized by COMT. If we go for 3,5-dihydroxy substitution, resistance occurs to COMT, which gives orally active compound. In addition, it provides beta-2 selectivity. Examples are metaproterenol, terbutaline, which are bronchodilators. Other substitution also provides oral activity and beta-2 selectivity, such as 3-hydroxymethyl group and 4-hydroxyl group on phenyl ring in albuterol. Actually, there must be at least one group capable of forming hydrogen bond. If that one group is present at third position, then it gives alpha activity. While if that one group capable of forming hydrogen bond is present on fourth position, it gives beta activity. For example, ritodrine, which stimulates beta-2 receptor in uterus and cause relaxation. Now, what is the therapeutic utility of adrenergic agonist and antagonist? Alpha-1 agonist cause constriction of vessels, so they are used in shocks, in hypotension and as nasal decongestant, while antagonists are antihypertensive agents because they relax or dilate the vessels. Now, alpha-2 agonists are antihypertensive agents because they inhibit norepinephrine release by feedback. They can be also used in glaucoma, since alpha-2 receptors are mainly located in CNS. Agonists are also used as analgesic and sedatives. Beta-1 antagonists are antihypertensive agents and antiarrhythmic agents, while beta-2 agonists relax bronchial smooth muscles, so they are bronchodilator and used in asthma and chronic obstructive pulmonary disease. They are also used as uterine muscle relaxant. Beta-3 receptors are present in fat cell. Agonists are responsible for weight loss as they stimulate the conversion of triglyceride to glycerol and free fatty acids. These are the references. Thank you.